actually like excited enough, psyched to continue without that. So what did we do before the break? There was some MPC, there was some in-the-head, there was all of this stuff. And I said, like, these are like some of the early results in the area. And I particularly mentioned this thing here. Oops, KKW, Katz-Kolesnikov 1, 2018 CCS paper that builds MPC in the preprocessing button. And it's kind of arguably the simplest way of building MPC in. And in the remainder of the time that I have now, which is 30 minutes, I'm going to do just that. Namely, explain how it works. And it's actually fairly simple. Modulo, I've now seen like so often that like yeah. So yeah. Anyways, so how do we actually model computation? It's like something that we have to think about before we can build an MPC scheme. And the way how it's going to be done is that we model the computation, like the evaluation of a circuit on some witness as follows. We're going to say that so the circuit consists out of gates, fan in 2, fan out 1, 2, many. And then what's going to happen? Well, the witness, these are just field elements, or some field, whatever you like in the field. And then each field element is going to be initially be fed into some kind of into some gate, like addition gates or multiplication gates. We have a field, so these are the two operations that we have. And then we evaluate that these gates here, like they get as input the witness, they are going to generate an output. That output is going to be fed as input into some other gates, and so on and so forth, until in the end we get the output of the output gate. Okay. And then that is 1 or something else, or 0, whatever. Okay, so far everybody with me? So what are we going to do? To build an MPC scheme, all we need to do is we need to set up a secret sharing for the witness, right? And then we're just all we're going to do is like figuring out how can I add 2 secret sharings such that the output is also a valid secret sharing, and how can I multiply 2 secret sharings so that the output is a valid secret sharing. And then like this is engineering approach, right? So we define the secret sharing, we define the elementary tools. The rest then just by composition becomes makes it possible to evaluate arbitrary circuits based on this. You have addition, you have multiplication, you have everything. And then we just have the secret shares be sent to the verifier, who reconstructs them and checks if they're valid in the end. Like that's all that happens. Okay, so far everybody with me? Fantastic. So these are the 2 things that we have to build, and we're going to build them in the dumbest way possible. So there is a circuit here, right, over some field, and we assume that there are n parties. Some n, being at least 2. No, at least 3. And so what do we want to have? Well, I want to have privacy against n-1 parties being corrupted. Like, even if I open all but one of the parties, I will not be able to learn a secret from the secret shares that I have. But at the same time, I don't really care about robustness like at all, ever. Like any party that can cheat can ruin the output. I'm okay with that. We will see why this is not a problem. Okay. Cool. So far so good. So how do we build the secret sharing? We're going to build it in the simplest way that you can imagine. Forget Shamir sharing, forget whatever. What are we going to do? n-1 out of the n parties just get a random value. And for the last party, we take the secret that we want to secret share over the field, and we just subtract all the secret shares from everybody else from it. And that is the secret sharing of the last party. That's it. So what happens if I add all of these together? Well, this term here cancels out and I get back x. And what if I pick any n-1 out of these secret shares? Well, these here are all uniformly random. And for this last one, you can argue that it's essentially a one-time pad of the secret. So that's also uniformly random if you see only like n-2 of these. So, you know, I have a secret sharing that is private against n-1 corruptions. It's like it's called the sum sharing. It's like the simplest secret sharing that is out there. Okay, we have a secret sharing. That was the first ingredient. Now we just need to realize the addition and the multiplication gates, and then we're done. Right? Then there's like only commitments, and we saw you can build them from hash functions. Oh, like that was it. Okay, nice. So how do we do addition with this, or like linear gates, that maybe multiplication by 2 or 3 or whatever field elements, addition of a field element? We get them for free. We don't even have to do anything. And that's because this is what is called the linearly homomorphic secret sharing scheme. Right? So if I have shares of 2 secrets here, I can add them locally together. Okay. And if every party does that, and everybody sends their sum, and like these terms just add up here, it's just, you know, it just commutes, and in the end you get just the sum of the values that were shared to begin with. You don't even have to do anything to do linear operations. Like you don't need to send something to somebody else. In the multi-party computation scheme, you just locally do whatever you want, what you're supposed to do. The same goes generally for multiplying with constants from the field, or for adding a constant from the field. Like all of these things you can do just by local computation, no interaction needed. So yes.
What's division by n mean here?
This is just so everybody does the same thing.
Okay.
If everybody adds the same constant, then you have n times that constant in the end in your sum, right? If you reconstruct. That's why. But you can always divide by n because you're in the field, and
Okay.
it just so everybody does the same thing. Otherwise, you would have to say party 1 adds the constant, everybody else does nothing. Okay. Good. So sum sharing is nice because, well, the sharing is super trivial, and linear operations are also super trivial. So now we just need to do multiplications, and then we actually build an MPC, a zero knowledge proof system. Okay. And we're going to do multiplications also in the easiest way that one can imagine. And for this, we use something called Beaver's trick, or Beaver's circuit randomization technique. So that was something that Donald Beaver came up with in the early 90s, which has been largely ignored for some time, and then like in the last 10 years or so, essentially became the foundation of all efficient multi-party computation schemes that are out there, because it reduces the task of doing a multiplication to doing linear operations. And we just saw that linear operations are for free. So here we go. And how does it work? Well, in order to multiply 2 secret sharings, you assume that you have a secret sharing of 3 random values, where A and B are just uniformly random, and C is the product of both. Okay. And those are secret shared, lying around somewhere, coming from a trusted third party, being provided as correlated randomness in the pre-processing model. Ta-da! That's why we need it. Mm-hmm. And once we have that, we can use those to multiply secret sharings of something else. We're going to kind of consume one triple, one of these so-called multiplication triples, to do a multiplication. Okay? Now, how do we do this? Well, we use the linear property to subtract A from X and B from Y. Okay, that's a linear operation, that's local. And afterwards, like, we call these things alpha and beta. And then afterwards, these are just like, everybody just reveals their share of alpha and beta to all of the other parties in the multi-party computation. Why is this fine? Well, A and B were chosen uniformly at random. So if we later reconstruct these, right, the verifier is going to see these. But we subtract something uniformly random from something that is secret, so one-time pad, security. You can easily simulate that. So we reconstruct alpha and beta, and then you just compute this linear expression here. It's like you multiply alpha with y and beta with x, and then do a bit more. And now you just like, you write this thing down, and magically everything disappears, and you end up with the product of x and y. It's just, yeah, it's just that, like you just write it up. And then you forget that it's the right thing. And every time you write down this formula, you make a mistake. Every time, every time. So there might be a mistake there. So if you find it, right, it's just what always happens. But the point is, so what have we done? Like we assumed that there is something that is a multiplicative correlation that we got from somewhere. And then we use this to do the multiplication of something else using only linear operations and sending secret shares to other parties in the multi-party. Right? So this needs some kind of interaction between these guys. We're going to pay for this later in some way. But that was it. We're done. We've built a multi-party computation scheme that can evaluate arbitrary circuits. Well, it's secure unless one person deviates from the protocol, but we can handle that. You know, we're not doing real MPC. We do MPC in the head. It's fine. Okay. So let's first, like, before we figure out where we get these multiplication triples from, let's figure out why we could assume that this thing is secure. Assuming that, like, the shares that we get of the multiplication triple. Okay. So if we open n-1 parties, it's going to be zero knowledge because I just said that, you know, the secret sharing can tolerate this many parties. It's still private. But we can never actually have that one party misbehaves. But well, if the prover is going to see n-1 out of the n parties, that means the verifier is going to see them. That means the prover can only cheat in one party. Okay. So if we do this game once, there's an n-1 out of n chance that the verifier is going to see the cheating party. If you cheat in two parties, you're always caught. If you cheat in 0 parties, you can't convince the verifier because you don't have the witness. So you need to cheat in one party. And what's the probability that this party will be opened? n-1 out of n. Okay. So we have a 1 divided by n soundness error. So now you just do parallel repetition again. Just do this thing in parallel multiple times, and you get any soundness that you want to have. Like the actual analysis is like a little bit more, like a tiny bit more involved, but it's basically that. It's just like it's the simplest way of doing a security analysis, like a soundness analysis for zero knowledge proof. Good. Now, what are questions before I continue?
What is the intuition here behind why parallel repetition is fine in this setting, and
we just have independent MPC in the head sessions,
and we don't have the issues of rewatch?
So we're just caring about honest verifier zero knowledge.
Okay.
And in that case, you kind of know who the verifier, like if you simulate, you know who the verifier is going to float later. And that's why. I should say there, once you start to build like practical multi-party practical zero knowledge proof systems, like this difference between zero knowledge, honest verifier, zero knowledge, arguments of knowledge and proofs of knowledge, like they all vanish and you just call everything a proof of knowledge. For all practical intents and purposes, people don't really care. For theory, though, it's very interesting to like go into the different details because you can find the corner cases where those will break down in practice. Yes.
Quick question. So this communication complexity doesn't look good at all. Can it be improved? Yes.
Like once we figure out how to put the trusted third party in the head, we're going to optimize the
You
communication.
basically sound like the computational trace of every single
You're going to see that there's not much that we will have to send. Like you can actually optimize a lot of this away.
Okay.
We'll get there in like 2 to 3 slides from now. Cool. Okay, everybody else. Oh yeah, we will be able to make that. Good. So first of all, we need to like get this pre-processing done. Right. So there's going to be some trusted party that gives everybody the share of their multiplication triples, and then the trusted third party walks away, right? And so we will just let the prover simulate this party here. Okay. Now, what's the issue? Well, the prover could send could generate correlated randomness that is not really correlated the way we would like to have it, and then we can't trust the output of the MPC, and you know, we actually we moved the problem like one level up, right? How do we check that, right? Before that, we had to check the multi-party computation. Right now, we have to check this trusted third party. But this is actually a problem that we can easily solve. Why is that? And it's because these shares are in this stuff here is independent of these secret inputs to the multi-party computation. So what are we going to do? If we do MPC-in-the-Head with preprocessing, maybe the simpler way is this. Go away. Is to explain it in the following slide. Okay. Let's say there are two instances of MPC-in-the-Head. For the sake of argument, we can make it as many as you want later. The prover is going to simulate both. And it's not going to start with the MPC protocol. It's going to spin up the MPC parties, and it's going to simulate two trusted third parties that are generating the correlated randomness. Okay? Good. So it has done that. And now it's going to commit to the randomness that has been generated here. And it's going to send the commitments over to the verifier. Now at this point, no secret input, no witness, no nothing. These are just samples from a distribution that the verifier knows like what it's supposed to be, okay? So what is the verifier going to do? It's just going to say, well, let's take the first MPC session and open me all the commitments, okay? And the prover is going to do that. And then the verifier can just check, well, do the samples from this distribution actually follow what they're like, actually follow the distribution or not, right? If there's a simple way to verify. Like in this case, I want that these things here like reconstruct to A, B, and C such that A times B is C. Like this is something that a verifier can do. And I, as the verifier, I can just get all of these. I don't learn anything secret here. Right? And then we're going to throw away this MPC-in-the-Head instance. Right. Now with a good chance, this one here was fine. Like here, the correlated randomness was fine, because if as a prover I cheat in all of these preprocessing instances, I will always be caught. So I can only cheat in some. So if we open a lot of them and we saw that the preprocessing was good, then in a lot of the other MPC-in-the-Head instances, the preprocessing must also be good. Same argument as we had before. So also just cut and choose. Okay. And then, since the prover has committed to the randomness here, like he then has to use this randomness in the MPC-in-the-Head relation. And that's it. Like that's how we get preprocessing into MPC-in-the-Head. Like that was the key observation by. It's like it's very simple, but yeah, making it's surprising that this then turns into such an efficient. Zero-knowledge proof system. Yes, you had a question.
Soundness 1/2, or
In this case, 1/2, but you can just spin up more of these instances. If you
to
want.
get 1/n?
Sorry?
To get 1/n.
No, you actually get something better, right? Because so if you generate more of these MPC instances in parallel, and I as a prover, let's say there are 500, okay, and we open 250 of them. Then if you cheat in exactly 250, there's a 1 divided by I think it should be around 1 divided by 2 to the 250 chance that you don't get caught. Okay, so you have to cheat in less instances, because otherwise there's a very good chance that you will get caught. Okay, but that means that there are a lot of MPC-in-the-Head instances we haven't opened where the preprocessing is actually good.
You do lambda of these or something.
Yeah, it's not constant. Like you need something like lambda or lambda. Okay, but now we're going to optimize a lot of the communication away.
You're opening certain MPC instances, and of each instance you're then opening like n-1.
No, so here we open everything, but we didn't do the MPC yet.
Okay.
This is before.
Just the
We just did the
preprocessing.
secret sharing.
Okay.
Yeah, it's just the preprocessing. And that's why we can make this actually very efficient. Okay, now comes the witness, then you do the MPC in. Okay, so let's start optimizing this, and then we'll see why this actually becomes a very efficient zero-knowledge proof system. Okay, so right? So the actual vanilla protocol is I send you a lot of commitments. And then I have to open all these commitments. Well, the dumbest thing that you can possibly do is to say, well, instead of sending you all these commitments, take your favorite collision resistant hash function, hash them all down, only send the hash. Why is that fine? Well, right, so I'm going to reveal to you n-1 of these views. You can recompute these commitments. I don't have to give them to you. You can recompute them like once you have the views of all of these parties. So instead of sending all the commitments, I just sent you a short hash. And for all parties that are opened, you just locally recompute the commitment yourself. For the party that we didn't open, well, I have to give you the commitment, but that doesn't give you any information, right? And this is a collision resistant hash function. So as a prover, that's the only thing I can do. Otherwise, you found a collision. Nice, right? So instead of sending all of these commitments, I just send you a short hash and all the rest can be recomputed locally. Yes.
Usually you have also some randomness into the commitment scheme.
Yeah, we can just for each view, just like the way how we're going to derive the view will just be that there's also there's a PRG seed involved that you can use to generate the randomness for the commitments. Okay, but yeah, we need that anyways. But okay, instead of sending a lot of commitments, just send one short hash, right? And if you do parallel repetition, that is even better, right? So instead of doing all, like if you have tau instances that where you do the MPC in the head scheme in parallel because you need to boost soundness to something negligible. Now, instead of sending all of these commitments, you now just send one hash, and then for each of these instances, you send a commitment. Because like there's always one commitment that the prover cannot, and that the verifier cannot recompute itself. And that's it, right? So we went down from like if you set n to a like this can easily be something like 2 to the 10, 2 to the 11, right? So if this is a factor 1024 and this is 16, right? So instead of 16 times 1024 times whatever the size of the commitment, you now get to something like 16 plus 1 times size output size of the hash function. That is already quite a substantial improvement. Yes, there was a question. You had a question? You had a question?
So John had a comment online. So on the previous slide, he said, you don't need randomness since everything is high mean entropy.
Yeah, that's true. That too, but if we just generically assume these to be commitments, then there should need to be randomness. In practice, each of these parties should have like there should be sufficient entropy in like whatever these parties are doing, because otherwise, like you could figure out what this party has been doing to begin with, and we're in trouble.
Yes, just to make sure, but now you run a lot of stuff on the verifier. So you pushed a lot of communication complexity to the verifier computation complexity.
Yeah. No, but actually, like look at it from the following perspective. You still recompute the whole view anyways, and then you just hash it down. So I replace what I let the verifier do is do SHA-256 calls. And like on your modern CPU or whatever else you want to use for that, and your modern CPU might have like built-in instructions for doing that. We're using for SHA. I think, do we have SHA? Does AES-NI have not AES-NI, but does a modern Intel CPU have instructions for SHA? Does anybody know? It does.
But what's the point again? Like, does it save you from recomputing?
It's not much. No,
one?
but you have an optimized instruction on your CPU that does that for you. So yes, there is work that you make the verifier do more work. It's not more work than the prover did, because the prover also had to do all of that. Yeah. The verifier has to do a bit more work in terms of hashing, but if you can leverage like built-in, like now we're talking about concrete implementation. If you can leverage like processor instructions that do this very fast, you don't really care. Like this is a cost that is somewhat negligible in comparison to all the rest that you have to do.
I mean, also it's like only tau plus 1 function cost.
Yeah, like if you're doing that with yeah, I mean if you set up, if you do Merkle Damgard or whatever, then it's just not so bad in comparison to all the rest that you're doing. And now there was also the point that, well, you have to open all of these views for all of these parties, right? That's a lot of random stuff that you're sending to the verifier. But, well, so the prover, so we had that like n-1 out of the n shares are generated uniformly at random, okay? And only the last share has to be adjusted to something specific, right? And for the multiplication triples, it's even nicer. Like all A and B, everything can be random. And only for C, one party's share has to be something that is not random, right? Because otherwise, of course, there's not really a useful correlation. These are all uniform. We are cryptographers. What do we do when we see this needs to be uniform, right? Well, why not do it pseudo-randomly instead? So instead of generating like each party's view, like instead of calling your local OS's randomness generator to just generate all the shares, instead you just generate the seed and derive all these seed from all the shares actually from the PRG seed. So for each of the parties 1 to n-1, almost all their view, all the shares they initially have, and so on and so forth, is just PRG applied to this. So if I want to open this party to the verifier, I just give the party the seed. And if it's, for example, if you have 3 parties and parties 1 and 2 are this way, right, are opened, then I also don't have to send, like if I have to open a view, I don't have to send what party 2 sent to party 1. If I open the seed, the PRG seed of party 1 and party 2, I can locally reconstruct that stuff too. So most of the communication, most of the stuff that is inside a view can be recreated from a PRG seed. So openings are also now just PRG seeds and a bit more. That is really neat, right? And now even more, instead of giving you everybody's PRG seed for every party, I can also shrink that down to something even smaller. So how does that work? So this is something that is called a GGM tree. Who has seen a GGM tree before? Only half of you. And I promise you that after this, I'll have to shut up because Peter also wants to say something. He's like very excited to talk about voles and heads. But he's going to need GGM trees, I'm afraid. So I have whatever time I need to explain this. Nice. Okay. So we take a length doubling PRG, and now we have n parties, and we want to derive all their seeds. Okay. And instead of just sampling all of these parties' seeds separately, we're just going to we take one seed, we have a length doubling PRG, we're going to stretch this into 2 seeds, apply the PRG again on those on the outputs. Now we have 4 seeds, apply the PRG again. Now we have 8 seeds. Nice, right? So we're just stretching something that is random into a longer string that is pseudo-random. It's called GGM construction. Okay. Now here's the thing. I'm going to reveal to the verifier all but one of these seeds, right? I'm going to, like, if the verifier says, like, don't open party 3 to me, but everybody else, I need to give the verifier 7 seeds in theory, right? But the thing about a GGM construction is I can do better. The reason is, so instead of giving here the verifier this seed, and everything else here, we can also do the following observation. Well, everything here can be recreated from this seed. So I don't have to reveal to the verifier all of this. I just give the verifier this. Instead of 4, I sent 1. Neat. So for this side of the tree, well, I don't open 3, right? But I open 1 and 2. 1 and 2 are both derived from this seed here, so I send the verifier this seed. And here I just give the verifier, like here I actually have to give the verifier this. Okay. Now it turns out, if we do this, then instead of n seeds for n being 8 here, I only have to send log n seeds to the verifier. So I get an exponential improvement in the number of seeds that I have to reveal to the verifier. And that's a huge other like in practice, like this is like a huge source of communication, and that's a huge improvement that you're having. Okay, everybody understands that? Yes.
I mean, like a fancy name for that would be like punctured PRF. Or
Yes.
is that something that's useful in that context?
Yeah, I mean, if you construct volts, then you actually rather talk about punctured PRFs than GGM trees. But I mean, I guess punctured PRF and GGM tree are essentially synonymous, right? So is there another construction for a punctured PRF? That's probably, yeah. Like if we care about practical efficiency, which is what I care about in this context, then that's the same. Okay. So that was that. Right. So and now if we do parallel repetition, right? So if we have n parties and tau repetitions, like instead of tau times n seeds, we have tau times log n seeds that we're sending. So if we even squeeze that down. And now just to also shamelessly advertise my own work, which has recently been accepted at Asia Crypt this year. Now, so we looked at this and thought, well, this is also kind of inefficient. So why is that? Because like you do this separately for all of these repetitions, right? So for every MPC instance that you do an MPC in the head, like you in parallel, like you derive the seed there this way. So let's look at two MPC in the head instances, right? You could argue, well, for both of them, I can recreate the seed from, oops, one seed up here. Okay, I can do the same trick. And this is now just to argue what we could optimize. But now we're in a very bad situation, which is now we always open exactly one, like we always not open one leaf in both of the subtrees. So this is the worst case if you think about GGM trees. And why is that? Well, that's because we defined that those leaves here all belong to the first MPC in the head instance, and those leaves here belong to the second MPC in the head instance, right? There's always going to be one leaf not opened here, and one leaf not opened on this side. Okay. Sorry? Yeah. Okay, good. Okay. So a very stupid, but in practice very neat observation is the following. What if we relabel these things here at the bottom, right? So instead of saying we do everything here for the first MPC in the head instance and everything here for the second, we do the next best thing. First party in the first MPC in the head instance, first party in the second instance. Second party in the first instance, second party in the second instance, or any kind of permutation on the leaves that you want. Okay. And now what happens? Well, if you, for example, never open party 3 in both of the MPC in the head instances, right? Before that, that means well, you're still in the scenario where, like, you know, there are two paths that you cannot open, right? You have to reveal anything. Now you have the situation, they lie next to each other. What does that mean? Well, I can open this whole tree. I can open this whole tree by just sending one seed, and this thing here, right? So before that, we were in a situation where we had to open 1, 2, 3, 4, 5, 6 seeds. Now we're down to 3 seeds. 1, 2, and 3. So simply because not opening parties can now actually lie in the same part of the tree, that allows you to send less communication. Yes, please.
This is the best case, and that previous one is the worst case.
Exactly, right? So in practice, they're going to lie in the middle, but if you're just shaving off a factor of 2 or even 1.5 of the number of seeds that you're sending, that's already quite a lot in practice. Like we're talking about optimizing like concrete protocols there. Like so, I mean, in practice, that what does it shave off? Like for the MPC in the head scheme that Peter's going to talk about in the moment, and I'm stealing all of his time. So this is just some, like, let's say like 500 bytes down to like maybe a little bit more that you can save, plus some other optimizations there. But if you talk about like proof sizes of 5 kilobytes, like now saving 500 bytes is like 10%. Well, that is something substantial in practice. Just for a like simple theoretical observation. Okay, that also means I'll only say one more thing before I hand over to Peter, which is the following. So, well, why do I spend so much time like talking about this specific stuff, right? So your communication, it still scales in the size of the circuit that you're evaluating. Like you don't get something that is sublinear in the size of the circuit. Well, the comment like for each multiplication gate, the communication is essentially like 1, 2, 3 field elements. So it's really small. So in terms of concrete overheads, like for the like the proof size, you really get something that is only like a little bit bigger than the circuit that you're evaluating. Like there's no big setup costs. Like if we see something like Starks or Ligero, if you heard of that, like there's a huge setup cost that you have to do before these things actually become efficient. And they are also like super fast when you do something here in practice. Like all of this field arithmetic is like super simple to implement on a CPU, and the rest is hashing and PRG calls, which is also very cheap to do on a CPU. So this stuff is actually concretely really efficient. And why do we care about them? Well, I unfortunately don't get to my second slide deck, but we'll put them online, which is there's the standard transformation which turns any kind of identification scheme into a digital signature scheme that uses a non-directive zero knowledge proof. You can easily make this kind of proof system non-directive via Shamir transform. You've heard about that yesterday. So we can build a signature scheme using these kind of proof systems. If we find a very simple identification scheme, and it turns out that you can actually build this using something as simple as AES, and now everything that you use to build a digital signature scheme are symmetric key assumptions. That's all we do. No discrete log, no lattices, nothing fancy. Sorry, lattice fans. And it turns out that like signature size is like 4 or 5 kilobytes. Sign verify times, you can get this down to single-digit milliseconds. So this is not so bad. It is quite competitive with other signature schemes out there, and you only make symmetric key assumptions instead of structured lattices or multivariate quadratic polynomials or whatever is fancy these days. So actually quite nice for like something as generic as this technique. Yes, one more question.